Let's talk about electric potential energy and its close cousin, electric potential. We'll begin with the more familiar gravitational potential energy. We know that a massive object raised in a gravitational field has potential energy. When the massive object is released, say by the cutting of scissors, snap, its gravitational potential energy transforms to kinetic energy. Energy is conserved in the process. So it is with an electrically charged particle positioned in an electric field. When the particle is released in the electric field, snap! A lowering of its potential energy equals a gain in kinetic energy. Again, energy is conserved in the process. Recall in a study of mechanics that the amount of work done on an object can change the energy of that object. That's in accord with work, which equals the product of average force and the distance moved. Consider compressing a spring. The work we do increases the potential energy of the spring. Here's a positively charged metal sphere. And here's a small charged particle, say a positive test charge. In this position, relative to the charged sphere, the particle has potential energy. Now we push the particle closer to the charged sphere, and its potential energy is increased. What's happened? The work done, the average force times the distance moved, increases the potential energy of the particle. Got it? The particle has more potential energy closer to the sphere than it had farther away. Makes good sense. Now, if the charged particle is released, it will be repelled and fly away from the sphere. Potential energy transforms to kinetic energy. Let me ask you a question. In its flight, it passes its initial position. At that initial position, how will its gain in kinetic energy compare with its decrease in potential energy? That's right. Its gain in kinetic energy at this snapshot point will be equal to the amount its potential energy decreases. Again, conservation of energy rules. So far we've considered electric potential energy. Here's a charged sphere again, and we indicate its electric field. I want to lead you to a more important concept in electricity: electric potential. Again, consider a test charge in the field of the charged sphere. At any point, a greater quantity of charge means a greater amount of potential energy. But get this, not a greater amount of potential energy per charge. 2 times the charge gives 2 times the potential energy. 10 times the charge gives 10 times the potential energy. 2 divided by 2 is no different than 10 divided by 10. Whereas potential energy is measured in joules and charge is measured in coulombs, the ratio of potential energy per charge is measured in joules per coulomb. Our definition of electric potential is the ratio of potential energy per charge. We call the ratio joules per coulomb volts. Whereas potential energy is measured in joules, straightforward energy, electric potential is measured in volts. 1 volt equals 1 joule per 1 coulomb. A question: what's the value of voltage for a coulomb of charge with a potential energy of 12 joules? Did you say 12 volts? That would be nice. Then we see that 12 joules per coulomb equals 12 volts. And 50 joules per coulomb equals 50 volts, and so on. Let's continue. You'll seldom hear electrical types talking about electric potential energy. Instead, they talk about voltage, electric potential. If you rub a balloon on your hair, the balloon becomes negatively charged, like up to 5,000 volts, as shown here. That would release thousands of joules of energy if the charge were 1 coulomb. However, 1 coulomb is a very large amount of charge. The charge rubbed on hair is typically less than a millionth of a coulomb. Therefore, the amount of energy associated with the charged balloon is very small, even though the energy per coulomb, the voltage, is very high. A modest amount of energy divided by a tiny amount of charge produces a huge voltage. That's why being next to a 5,000 volt Van de Graaff generator isn't harmful, even when touching it. High voltage means high energy only if a great amount of charge is involved. More important are differences in electric potential, voltage differences, especially in electric circuits. Consider a common 12-volt automobile battery. Due to chemical reactions inside, a 12-volt potential difference is maintained between its two terminals. When a circuit is connected across the terminals, 12 joules of energy per coulomb pass through the circuit and through the battery. We've all seen birds perched on high-voltage wires. Why isn't this bird shocked? It would be if there were a voltage difference across its body. One foot may be at 1,000 volts, but if the other foot is also at 1,000 volts, no difference in volts means no shock. These ideas took me a long time to learn. I hope you learn them in a shorter time. Let's conclude with a question. Why is it a bad idea for our bird to reach over and make contact with another wire? What is likely different about the other wire? Until next time, good energy.